Welcome to our quantum deep dive. Today we're diving right into, well, a really revolutionary area, hybrid quantum classical generative models.
Yeah, it's where AI meets quantum computing. Pretty fascinating stuff.
Exactly. And our guide for this exploration is an insightful essay by Jorgo Schneeppat. His work is really the bedrock for this deep dive. So the mission today...
Basically, cut through the complexity, right? Give you a clear understanding.
Right. How these cutting-edge models are designed, what challenges they tackle.
And, there are immense potential for the future.
Think of it as your express lane to understanding a field that's, well, creating entirely new possibilities.
Mm-hmm. And maybe before we get to the hybrid part, we should quickly touch on the classical side.
Good idea. What are we talking about there?
Well, classical generative models, you've probably heard of things like GANs, generative adversarial networks.
Yeah, and VAEs, variational autoencoders.
Exactly those. Their whole aim is to create new, realistic data. So think images that look real, or text that reads naturally, maybe even synthetic voices.
How do they do that?
They learn the underlying patterns in huge data sets, and then essentially imagine new examples that fit those patterns.
Right, and we've seen some amazing results from them, almost like magic sometimes.
Definitely.
Yeah.
But they do run into problems.
Okay. Despite their power, there are limits.
Precisely. Especially when you push them towards really complex, high-dimensional data, they hit some fundamental roadblocks.
Okay, let's unpack this a bit. Before we jump into the hybrid solution, what are these classical generative models in a bit more detail, and why are they so challenging?
Sure. So their main goal is to learn the probability distribution of some data. Basically, understand the rules of how the data is structured. Then they use that understanding to generate new synthetic samples.
And that's different from, say, a discriminative model.
Yeah, exactly. A discriminative model tries to classify data like telling a cat photo from a dog photo. A generative model tries to create new cat or dog photos.
Got it. So tell me about GANs. How do they work?
Okay, GANs have this really interesting adversarial setup. You have two parts, a generator and a discriminator.
A generator and a discriminator. Like opponents.
Kind of, yeah. The generator tries to create fake data images, for instance. The discriminator's job is to look at both real images and the generator's fakes and decide which is which, real or fake.
So they're competing.
Constantly. The generator gets better at fooling the discriminator, and the discriminator gets better at spotting fakes. It's like an arms race.
And mathematically, that's like an optimization game.
Exactly. It's often represented as a minimax game, mathematically back DD, where G tries to minimize the value, D tries to maximize.
Okay, and VAEs, are they similar?
They're different. VAEs are more probabilistic. They use something called variational inference to learn a hidden or latent representation of the data.
Latent representation, like the essential feature.
Sort of, yeah. They have an encoder that compresses the data into this latent space, and a decoder that tries to reconstruct the original data from that latent code.
And there's a specific way they measure success.
Their loss function involves reconstructing the data well, but also keeping the latent representation close to a standard distribution, often using something called the Kullback-Leibler divergence. So the loss math call combines reconstruction error and this KL divergence term.
And are there others besides GANs and VAEs?
Yeah. Briefly, there are also flow-based models. They use clever invertible mathematical transformations to model complex probability distributions directly.
Okay, so all these models, GANs, VAEs, flows, how are they generally trained?
Typically, they're trying to approximate this underlying data probability key X using some model parameters. Let's call them theta. And they often use techniques like stochastic gradient descent or SGD to optimize those parameters based on the training data.
Right. Now let's get back to those challenges you mentioned earlier, the roadblocks.
Okay, so first, mode collapse. This is a big headache for JAMs.
Mode collapse. What does that mean?
Imagine you want the JAN to generate all sorts of different faces, but it gets stuck and only generates, say, blonde women looking straight ahead. It's collapsed onto just one mode or type of data.
So a lack of diversity in the output.
Exactly. It fails to capture the full variety present in the real data.
Okay, what else?
High computational complexity. Training these models, especially with high-resolution images or really complex data sets, takes enormous computing power. Loads of time, loads of energy.
Right, they need big GPUs and lots of patience.
You got it. And finally, optimization instability. Remember that adversarial game in GAN?
The generator versus discriminator.
Yeah. Getting them to train nicely together to converge to a good state is notoriously difficult. Sometimes the training just oscillates wildly or collapses entirely.
It sounds fragile.
It can be. That adversarial dynamic is powerful, but tricky to manage.
So you can see why, despite how powerful they are, these models kind of hit a wall sometimes. They struggle to really capture the full, messy complexity of real-world data distributions.
Absolutely.
Yeah.
And this is precisely where quantum computing starts to look really appealing.
Okay, let's pivot to quantum then. How does this new paradigm offer a potential solution?
Well, quantum computing is just fundamentally different. It operates on the principles of quantum mechanics.
Instead of classical bits, 0 or 1.
Right. We use qubits. And the key thing about a qubit is superposition.
Meaning it can be 0 and 1 at the same time.
In a sense, yes. It exists as a combination, described mathematically as alpha wrangle plus beta 1 wrangle, where alpha and beta tell you the probability of measuring 0 or 1.
Okay, superposition. What else is key?
Entanglement. This is maybe even more profound.
The spooky action at a distance.
That's the one Einstein famously mentioned. Entangled qubits are linked. Their fates are intertwined instantly, no matter how far apart they are.
And how does that help with machine learning?
This non-local correlation allows for a kind of exponential parallelism. Quantum computers can explore a huge number of possibilities simultaneously.
Like checking all answers at once.
That's a good analogy. It gives quantum algorithms a massive advantage for certain problems, particularly complex optimization and sampling from high-dimensional spaces, exactly the kinds of things generative models struggle with classically.
Can you describe the quantum state mathematically, briefly?
Sure. A quantum state is represented by a state vector, usually written on Cyrangle, in a complex vector space called a Hilbert space.
And you manipulate these states.
Yes, using quantum gates, which perform unitary transformations. Think of the Hadamard gate, for example, which puts a qubit into an equal superposition.
Are there specific quantum algorithms that are relevant here?
Definitely. Things like the quantum Fourier transform, QFT, quantum amplitude amplification, which is the basis for Grover's search algorithm, and crucially, quantum sampling.
Quantum sampling, that sounds directly useful for generative models.
It absolutely is. Quantum systems can naturally generate random numbers or samples from very complex probability distributions much more efficiently than classical computers in many cases.
Okay, here's where it gets really interesting for me. If quantum computing has these amazing capabilities, superposition, entanglement, efficient sampling, why not just build fully quantum generative models? Ditch the classical stuff entirely.
That's the million-dollar question, isn't it? And it leads us straight to the practical realities of today's quantum computers.
Okay, what are those realities?
We're currently in what's called the NIC era.
NISQ.
Noisy intermediate scale quantum.
Noisy and intermediate scale doesn't sound ideal.
It means our current quantum processors have a limited number of qubits, maybe dozens, hundreds, perhaps low thousands soon, but not millions like classical chips. And crucially, they're noisy.
Meaning errors.
Exactly. Qubits are incredibly sensitive. They lose their quantum state, decohere very easily due to environmental noise. This limits the length and complexity of computations we can reliably perform.
So building a purely quantum GAN to generate, say, high-res photos is just not feasible right now.
Not for complex, large-scale tasks, no. The hardware isn't robust or large enough yet.
Yeah.
We'd need far more qubits and much better error correction.
Which brings us to
The necessity of hybrid models. This is the motivation.
combining the two worlds.
Precisely. Leverage the strengths of each. Classical computers, especially GPUs, are fantastic at handling large data sets, doing lots of standard processing efficiently.
Things they're already good at.
Right. Then you bring in the quantum processor for the specific tasks where it offers a real advantage.
Like the really hard optimization parts, or that complex sampling.
Exactly. You let the quantum algorithm accelerate or enhance those specific bottlenecks within the larger classical framework. It's about optimal task allocation.
Can you give some examples of these hybrid approaches?
Sure. One area is quantum Boltzmann machines, or QBMs.
Quantum version of classical Boltzmann machines.
Yes. They aim to find low energy states, like classical ones, but they use quantum effects, specifically quantum fluctuations, to explore the energy landscape more effectively.
How does that help?
It can help them avoid getting stuck in poor local solutions and find better overall solutions, potentially faster. The Hamiltonian includes not just classical interaction terms like sigmas as, but also a quantum term like gamma sigmas that drives these fluctuations.
Interesting. What else?
There are quantum-enhanced GANs, or QGANs,
Using quantum bits in the GAN structure somehow?
either in the generator, the discriminator, or the training process itself, yes. The idea is to leverage quantum phenomena to improve training stability or the quality of the generated data.
And QVAEs.
quantum variational autoencoders. Here, the idea is often to represent those latent variables we talked about earlier using quantum states.
So the hidden code is quantum.
Exactly. This can allow for much richer and more compact representations of complex data patterns within that quantum latent space.
So what this really means then is we're building bridges, smart connections between classical AI and quantum mechanics.
That's a great way to put it. We're creating systems where they work together synergistically.
To solve problems that neither one could really handle effectively on its own.
Right. Overcoming the limitations of one with the strength of the other.
Okay, let's unpack this further. How are these quantum and classical components actually combined? What does the architecture look like?
It varies, but a common theme is using the quantum part to accelerate or improve specific subroutines.
Like speeding up training.
Yes. For instance, the optimization step in training many machine learning models involves finding the minimum of a complex loss landscape.
Yeah.
Quantum algorithms like QAOA, the quantum approximate optimization algorithm, show promise for navigating these landscapes more efficiently than classical optimizers for certain problems.
So the quantum computer helps find the best model parameters faster.
Potentially, yes, or helps find better parameters. Another key area is sampling.
We mentioned quantum sampling before.
Right. Generating samples from complex high-dimensional probability distributions is fundamental to generative models. Quantum computers can, in principle, prepare quantum states that represent these distributions and then sample from them very efficiently.
More efficiently than classical methods.
For certain types of distributions, yes, the advantage could be significant. Quantum mechanics can naturally generate probability distributions that guide how model parameters, like network weights, are updated during training.
Let's dive into QVAEs again. You said the latent variables are quantum states.
Correct. Imagine the encoder maps the input data to a quantum state in a Hilbert space. This quantum state is the latent representation.
And then a classical decoder takes that quantum state.
Well, we have to measure the quantum state, which gives classical information. Then a classical neural network, the decoder, uses that information to reconstruct the original data type, like an image.
What's the big advantage there?
Efficient modeling of high-dimensional distributions. Quantum Hilbert spaces grow exponentially with the number of qubits. This means a relatively small number of qubits can represent incredibly complex distributions in the latent space, potentially much more efficiently than a classical latent space of the same dimension.
Okay, and QBMs. You mentioned quantum fluctuations helping find better solutions.
Right. The Hamiltonian, which describes the energy of the system, includes that transverse field term, the Gemayel sigma part. This term essentially encourages the qubits to explore different configurations, allowing the system to tunnel through energy barriers that might trap a purely classical search.
So it explores the possible solutions more thoroughly.
Exactly. It can lead to faster convergence during training and potentially find lower energy states corresponding to better model fits.
Now, hybrid GANs, or QGANs, what might one look like?
A common architecture involves using a quantum circuit as the generator.
A quantum circuit creating the fake data.
Yes. The parameters of the quantum circuit are learned during training. This quantum generator is then paired with a standard classical neural network as the discriminator.
And the discriminator's job is still to tell real from fake.
Still the same job, yes. But the generator is leveraging quantum resources.
What quantum advantages might help here?
One is potentially more efficient random number generation for the latent vector Z.
The input noise that seeds the generator?
Exactly. Classical GANs usually sample Z from a simple distribution, like a Gaussian. Quantum processes can generate truly random numbers or sample from more complex distributions that might better capture the underlying structure needed to generate realistic high-dimensional data.
And entanglement. Does that play a role in QGANs?
It absolutely can. Entanglement allows for correlations between qubits that have no classical analog.
Non-classical correlation.
Right. Within the quantum generator, entanglement can create sophisticated links between different parts of the latent space or features being generated. This could allow QGANs to model intricate dependencies in the data more effectively.
Leading to better quality data and maybe more stable training.
That's the hope. By representing complex data structures more naturally using entanglement, QGNs might generate higher fidelity samples and potentially converge more reliably during that tricky adversarial training.
It's fascinating stuff, but it sounds incredibly challenging to actually build and run these systems. While the theory is compelling, what are the real-world hurdles?
Oh, absolutely. Implementing these is definitely non-trivial. The hurdles are significant.
What's top of the list?
Still error rates and decoherence. As we discussed with NISQ, quantum states are fragile,
Right.
noise creeps in, computations get corrupted. We need the quantum parts of the hybrid model to run reliably, and that's tough.
Computations have to be short and shallow.
Pretty much, for now.
Yeah.
And then there's the limited qubit count. Even if the quantum part only handles a specific subroutine, that subroutine might still require more high-quality qubits than we currently have available for complex real-world problems.
So scale is still a major issue.
A very major issue.
How are researchers tackling these problems? What are the solutions?
Well, for errors, there's a huge amount of research into quantum error correction.
Like building in redundancy?
Sort of. Techniques like surface codes encode logical information across many physical qubits in a way that allows errors to be detected and corrected, at least in principle, but they require a massive overhead in the number of physical qubits.
So we need better hardware too.
Definitely. There's constant hardware advancement. Researchers are exploring different physical platforms, superconducting circuits, trapped ions, photonics, topological qubits, striving for more qubits, longer coherence times, meaning states last longer, and lower error rates on basic operations.
And bridging theory and practice.
That's where strategies like quantum classical co-design come in, designing algorithms from the ground up to work efficiently across both types of processors.
Making the most of what we have now.
Exactly. And leveraging cloud-based quantum computing platforms is also huge. Companies like IBM, Google, IonQ, Rigetti, and others offer access to their quantum hardware over the cloud.
So researchers everywhere can experiment.
Yes, it dramatically lowers the barrier to entry for running experiments on real quantum devices, accelerating progress.
This really raises a big question. Beyond the technical challenges, assuming we can overcome them, what kind of impact could these hybrid models actually have? Where could they change things?
The potential impact is vast, really, across many fields.
Let's start with creative applications. You mentioned art, music.
Yeah, imagine QVAEs not just mimicking existing styles, but discovering truly novel aesthetic patterns because of how they explore the latent space, or generating musical sequences with harmonic structures that classical models wouldn't stumble upon.
More sophisticated text generation, too.
Potentially, yes. Creating narratives or poetry with deeper coherence or unexpected creative leaps, perhaps fueled by efficient quantum sampling.
Okay, what about science and industry? That seems like a huge area.
Absolutely critical. Take material research. Designing new materials or catalysts is often a search through an enormous space of possibilities.
A high-dimensional optimization problem.
Exactly. Hybrid models could accelerate this massively. QBMs might propose candidate molecules, and quantum simulations, perhaps run as part of the hybrid loop, could accurately predict their properties, like chemical stability or reactivity.
Because quantum mechanics governs those properties anyway.
Precisely. You're using quantum to model quantum. This could slash the time it takes to discover materials with desired properties for batteries, solar cells, industrial processes.
What about finance?
Another big one. Finance deals with complex systems and high-dimensional data constantly. Hybrid models could lead to better financial forecasting, more sophisticated risk management.
How?
Well, maybe using QAOA for optimizing complex investment portfolios, or using QGANs to generate very realistic synthetic market data for training trading algorithms or stress testing risk models. Quantum sampling could improve Monte Carlo simulations used for pricing complex derivatives.
And medicine, pharmacy, drug discovery.
Huge potential there, too. Drug discovery is incredibly slow and expensive. Hybrid models could speed it up dramatically.
By designing new drug candidates.
Yes, and crucially, by simulating how those candidates interact with biological targets like proteins much more accurately.
Simulating the quantum effects in chemical reactions.
Exactly. Accurately calculating things like binding affinities, how strongly a drug molecule sticks to its target, requires solving the Schrödinger equation for complex molecules. Quantum algorithms promise a way to do this for molecules far beyond the reach of classical simulation.
So faster discovery of more effective drugs.
That's the dream. And maybe even personalized medicine, designing drugs tailored to an individual's specific biochemistry.
What's the long-term vision? Will we eventually ditch the hybrid part?
Perhaps. The aspiration for many is fully quantum-based generative networks, quantum neural networks, quantum generators and discriminators once the hardware becomes powerful and fault-tolerant enough. But that's likely quite far off. Hybrids are the crucial bridge for the foreseeable future.
Now, with all this power, we have to talk about ethics.
Absolutely essential. We can't ignore the potential downsides.
Like what?
Well, the ability to generate even more realistic fake content, deepfakes, is a major concern. Misinformation, fraud, the potential for misuse is serious.
And who's responsible for the output of these models?
That's a huge question. If a hybrid model generates harmful content or makes a damaging prediction, where does the responsibility lie? With the designers,
Yeah.
the users, the model itself? It gets murky.
And
Another key point, there's a risk of a quantum divide if access to this powerful technology becomes concentrated geographically or economically. We need to think about equitable access.
so responsible development is key.
Critical. We need ongoing discussions about ethics, proactive development of safeguards, and potentially new forms of regulation to ensure these technologies benefit humanity broadly.
Wow, what an incredible journey we've taken today. We've explored how Jorgo Schneppat's work really highlights this amazing synergy, this powerful combination of classical AI and quantum mechanics.
Yeah, these hybrid models are genuinely exciting. They're not just small improvements. They represent a new way of tackling problems that seemed almost impossible before.
Really bridging the gap between the AI we have now and the quantum future.
Exactly. It's about making progress now, even with an IceQ hardware.
So as you reflect on this deep dive, here's a thought. Imagine a future where these hybrid systems don't just create that stunning new art or design those life-saving drugs. What if they also start revealing entirely new insights into the fundamental nature of reality itself, just through the unique way they compute and model the world?
That's a mind-bending possibility. Using these tools not just to engineer, but to discover.
What incredible possibilities could that unlock for us? Something to think about. For those of you eager to explore further, you can find more information about Jorgo Schneppat's insightful work and related topics at schneppat.de.
Definitely worth checking out.
Thank you so much for joining us on this deep dive. Until next time.